Okay, okay, Marta, do you think we can start or do you want to wait a little longer?
No, I think we can go on. Yep.
Yeah, wonderful. And I know, and I like the this kind of group size because it makes it easier to talk and interact and which is the purpose of this. So my name is Michele Zanolin, and I used to be the chair of the LIGO Virgo Supernova Group, and I work predominantly in data analysis for core collapse supernovae, but I also have some interest in the theory and in the experimental side, pretty much everything that is helpful for the development of the supernova program. That's what I do. And I prepared the slides with Marek, which is a former student of mine. Now he's the head of the gravitational wave group at the University of Warsaw. He just got his faculty position a couple of weeks ago. No, a couple of years ago. And so we put together the slides. So what I wanted to cover today, and please, stop me for any question and discussion because I know that the point is to improve the interaction of the communities. Is I wanted to discuss a little research effort, part of the reorganization that we have going on in the LIGO Virgo cargo community, and to better interface with the different branches of the supernova research program. And then there was a question about specific searches. So I will say a little bit about some of the specific searches. And then I wanted to talk about something that people might not have seen much, which are a lot of current trends in parameter estimation for core collapse supernovae, different methodologies that are under being development. And if anybody here has any idea on how to extend some of the things that I mentioned, please contact me offline and I'll be happy to talk about. And I will mention a little bit some of the future plans. Uh, this is going to be kind of a overview talk. If someone wants to have an intermediate level of depth, I circulated to Marta the review paper that I just finished with Mezzacapa for physical review letters, no, review of modern physics. And we pretty much summarize about 300 papers involving the theory and data analysis of core collapse supernovae. It's almost impossible to summarize everything, but we try to give a good glimpse of the landscape. So the first thing I wanted to mention, which might be of interest to a number of people, is that I know the LIGO Virgo cargo is undergoing a transformation. We are going through a transition from three different collaborations to, for the data analysis part, like a single collaboration that is going to be called IGWIN, and the experimental side is still going to be handled separately. But this part of this transformation is also to have a better interface between the different aspects of the supernova science and improve as much as we can the multi-messenger aspects of the science. And this is one of the reasons why I'm happy to come to these calls. And we have this kind of calls. We just started this kind of calls also in the LVK. So we will probably invite people from SNEWS and the neutrino community to come to our calls. And the current chair, Marco Cavaglia, who's at the University of Mississippi right now, actually Missouri, will probably do some invitation. But anyway, so the National Science Foundation asked us to have a more structured effort to improve the coordination and the development of the methodology for multi-messenger science in core collapse supernovae. And the first thing that we decided to do was to organize this symposium. And so a lot of the material that I will mention and more is available at this symposium. The central masses was about having theorists and for the do modeling for Cocola supernovae, and we had the Garkin group, the group from Oak Ridge. We had people from Princeton, Japan, and many groups were there, and data analysis. But we also had a representative from the neutrino side. I know John Beacom was there, and electromagnetic observers. I know it's a big, ambitious enterprise, and hopefully we're gonna be able to organize these conferences regularly. But I know I would encourage that if someone has anything that captures their attention, to go and look at some of the talks for the specific areas. We are just starting, but it was a good start. We had 100 people, and these are the location where people came from. So I know if you have any interest, on anything, look at that. But again, I hope this is a beginning of some conversation. And some of the lessons, and we're in the process of writing a white paper, is what are the priority in the coming years, and I'm not gonna go too much into detail, but an important one is to have a little more of an organized plan of what we would do in the case for a galactic core collapse supernovae in combining neutrino, electromagnetic, and gravitational waves. But there is also more coordination that can be done for other aspects, and I know, for example, the theorists in the last few years, they've been very good in making available the gravitational wave signal produced from hadronic matter, but rarely they include the neutrino contribution, and rarely they make neutrino contribution available. Sometimes it is made available, sometimes it's not. And I understand that is related to the evolution of the simulation and how much people go in depth, including the neutrino physics and neutrino transport and all the details of the astrophysics related to neutrino physics. And some groups feel comfortable about the end production of the gravitational wave, but sometimes they're not exactly comfortable in sharing the neutrino luminosities. And I hope that evolves as well. But anyway, so let me say a few words about the searches from core collapse supernovae. So this is broadly included in the whole plan of gravitational wave searches, and for the LIGO Virgo community, Kagra community, and we are roughly divided in short or long and templatable and non-templatable. And historically, the supernovae has been in this part that are short and non-templatable, even if some parts are becoming templatable. For example, for rapidly rotating core collapse supernovae, the core bounce has free peaks that are deterministic, and they depend on mostly on the ratio of rotational versus kinetic energy, the beta parameter, but also on the equation of state. And there are already papers, at least my group has a couple of papers out on how to do a match filter search just for that part. There is also another part which is templatable, that is a new aspect, which is the memory component produced by core collapse supernovae. And in that case is the first part of the waveform that is visible, the ramp up in developing the waveforms. And again, there is a paper out, and I will show some of the references in physical review letters, where we show for the first time that ground-based interferometers can detect this signature. It is expected that, I know, if you would be able to build an instrument on the moon, you might be able to detect it as well, because I know there is larger signatures, and even space telescopes could have good potential for that. But I know in my talk, I'm gonna mostly focus on the discussions for the existing and future ground-based interferometers. So when we look for supernovae signal, we have two types of searches. We have the targeted search and the all-sky search. The targeted search is expected if you have an electromagnetic interesting candidate or a neutrino candidate, which we know that the next galactic supernova has already exploded, but we don't know when they will arrive to us. And we also, and these are searches that we do when the light curve is known sufficiently well to constrain the interval of time where we think the gravitational wave might have reached us. And constrain sufficiently well, it means ballpark of a week, few days, maybe 12 hours, I know, but not too much longer, because if it becomes several weeks, you don't have much more benefit compared to search a whole run, which is of the order of a year. Then there is the all sky search that I know that searches all the data and is not as sensitive, but I know you might be able to catch something. For example, if there is some obscured supernova from dust and I know we expect gravitational wave to arrive anyway. So we have a certain, probably broad variety of pipelines that and approaches. I know almost all of them are based on doing some wavelet decomposition of the data and forming cluster of unusually energetic wavelet components. And what varies between different pipelines is if they use any frequentist approach, which is the one of the current I know, flagship pipeline coherent wave burst, or I know a Bayesian approach. The Bayesian approach, you have to be careful in using that because the prior are needed, and if you develop prior on the noise, it's a fair statement. But if you develop priors on the parameters, that's not a fair statement because we don't know the distribution of parameters for supernovae, and the prior have an impact on parameter estimation. And someone says, well, you can do Bayesian with uniform priors, and it's a very delicate process because if you estimate the amplitude, you could say, okay, I can assume the amplitude of a wave is uniform, the prior. If you estimate the energy, you can assume that the prior for the energy is uniform, but a uniform in amplitude is not uniform in energy, and a uniform in energy is not uniform in amplitude. So no matter what is your uniform prior that you assume is going to have non-trivial implication for some of the parameters. And but anyway, so these are examples of things that are developed. And I know, as I said, they're all based on some kind of wavelet transformation and forming some cluster of energetic wavelets. And this is an example of how a gravitational wave might look when it goes through coherent wave burst. I know you have I know clusters in time and frequency of energy, and you have to use this cluster both for detection and for interpreting the results. And I will talk about it. Typically, I know the way it works is that each of these events gets assigned some kind of metric for the energy, and then you calculate how likely it is to have that quantity, that size of the metric. If you just look on background events, and if it's sufficiently rare, you declare a detection. And we are at the stage where I know for a good variety of waveforms, we can already detect the signature in the galaxy, not all of the possible waveforms. And maybe that will never be reached because if you have a supernova that is particularly spherical, the quadruple emission is going to be very, very weak. So, but I know we already have a broad range of results on the type of waveform that we can detect. I know the most recent published one is for the O3 search, and these are the supernovae that we processed. That the results is already published, and we didn't detect them, and we produce a number of metrics like I know upper limit on the energy, model exclusion probability, where we use a supernovae to exclude some of the most energetic models. And this is just to give an example of how this operation works. So we look at the light curve, and in this case, I know is the 2023 IXF. This is actually the only published one, part of O4, and we try to estimate the time of the sharp breakout. And this is a lucky one in the sense that the observation started pretty much the time of the sharp breakout. Usually, you start seeing the light curve, a few days to a week after. And if it's a few days, a few week after, then we try to do interpolation methods that we tested. Currently we're using a quartic polynomial in the intensity, but there are other ways you can do it. You can also do interpolation with methods that are physics-based, where while you do interpolation, you also estimate properties of the parameters. We don't do them in-house, but we collaborate with people that do them, and we take what is out there. It is a delicate business. Why? Because even when you calculate the time of the shock breakout, then the gravitational wave is expected to be happening before, and is at the time of the collapse, and the time of the collapse is before the time of the shock breakout, and the temporal separation of the two needs to be estimated or quantified in some form. This is for IXF was where the light curve was, and the box at the top left indicates where we search the data, and the red and blue color indicate while the interferometer were collecting data. So the yield at the end might not always be as good as you want to. But what I wanted to stress, and this is something where I think is good if we have a coordination between different communities, is the issue of how back you go in searching the data from the time of the shock breakout. And this paper illustrates the issue. So this is a paper from the group of Shankouch, where they varied the progenitor mass. Even if the horizontal scale says ZAM mass, this is actually the progenitor mass right before the explosion. And they run some simulations where the physics progressively simplifies during the evolution in such a way that can run the physics for 3 days at a time. And it is a reasonable assumption. I know obviously the first 2 seconds you have to have all the physics you can, but I know that it is reasonable to expect this physics simplifies. But the main point is that the delay can vary. I know you can go from in this analysis, and is the most accurate, the most extensive I've seen. It can go from 1 days to 5 days, and if you know that your progenitor has a mass that is below a certain value, you can constrain it more. For example, if you know your progenitor is below 15 solar masses, there are good chances that the delay is less than 2 days. But if you don't know that, it could be 5 days. So the reason why I mentioned this is because I noticed at certain point when we had the 2023 IXF, Super Kamiokande released a statement where they said that they didn't see any neutrino corresponding to the observation, and they used a window in checking for the presence of neutrino, which was, I think, like a couple of days before the time of the shock breakout, which might not include all the possible delays that you have between the shock breakout and between the collapse and the shock breakout.
Yeah, actually, that's what I was thinking looking at this plot, is this is way longer than we ever think about in terms of the neutrino world, where for a really bloated star like Betelgeuse, it might be on order of a day and a half. And all other stars are much less than that. I'm very curious why the difference.
Yeah, so this is a beautiful area. Let me just say a couple of things, and then obviously we can discuss it even further. So what are the issues? So there is one issue where, and I was talking about this with David Sand. There is the idea that in the local universe, people have been seeing fairly rarely light progenitors. There is this red giant problem where they say they can't see progenitor with more than 17 solar masses. If that's the case, that seems to indicate that you go toward the light mass. And then there is the issue that I talked with Sean Couch, which is that, and this goes in the next slide that I might discuss your point, is that it seems that in the electromagnetic community, there are 2 camps. There are some that estimate the mass of the progenitor using the early part of the light curve, and some that use the plateau. and they tend to get very different estimates of the mass. And here I give them some example of one group that says, oh, it's between 8 and 10 solar masses. And the other group says 20 plus and minus 4. And if you look at the papers, they don't comment each other's work. They don't say, oh, I think mine is more accurate for this or that, or I'm concerned about the systematics of the other approach. They just ignore each other, and which makes it really hard for us. So that's why, for example, in our community, we just use 5 days. But that's also one of the reasons why we would like to have more discussions between the community to understand a little bit where things are standing. So I don't know if this helps a little bit your question.
Actually, do you mind if I just interrupt here?
Sure.
Sorry, this is Jeff Zung. I'm at Oxford. I mean, yeah, I mean, I was also struck by this plot. And I was also just wondering, how are you defining, I mean, when you define the delay, I guess, there's a delay to the shock breakout, which is well defined, but what do you define as the beginning of the gravitational wave?
So that's a good point. So keep in mind that I know we are the gravitational wave emission and the bulk of the neutrino emission, they will be apart, I know, tens of milliseconds at the most, right? So the collapse and the gravitational wave emission and the neutrino emission, they'll all be very clustered. If you say a second, just to be generous. And the uncertainty that you have on the time of the shock breakout, maybe, I know, if you look at a plot like this, I don't know, maybe order of an hour, okay? And now, so if you define, there is some fuzziness in defining the delay between the gravitational wave emission and the neutrino emission, the time of the shock breakout, but the fuzziness is of the order of an hour, if you want, or 2 hours. I know this plot on the other side, it shows that the total delay between the two can vary order of days. Okay, so the problem is, I believe, is not in the fuzziness of the delay between the gravitational emission, neutrino emission on one side and the shock breakout, is to understand what is the actual range of delays you could have. And I wish more theorists would try to reproduce these plots with different simulations. But on our side, internally, just to be safe, currently we use 5 days. But I don't know, we say, I know, if we would be able to constrain the mass of the progenitor better, we might reduce it. I don't know. Does it answer your question?
Well, probably. I mean, I'm actually wondering if the answer was kind of in the middle of what you were saying. Maybe I misunderstood this. Did you say that, or did you indicate that you might say the largest neutrino burst, right? The peak luminosity for neutrinos, or which is reasonably close to the shock breakout.
No, the neutrino burst is extremely close to the gravitational wave. The neutrino burst is going to be days before the shock breakout. You have
Oh, sorry. Yeah, okay, that's right. I keep on forgetting the
yeah.
two different terms. Right. So comparing the gravitational waves plus neutrinos and then taking that delay to the
Shock breakout.
electromagnetic, that's what we're actually talking about here.
Yeah. The vertical axis here is that assume that the neutrino and gravitational wave, they're roughly the same time within a second, or even, I don't know, people might say 10 milliseconds, and then 12 hours, 20 hours of days after, then you have the time of the shock breakout.
Yeah. Okay. Thanks. Yeah, thanks for clarifying.
Okay. And I go over to bigger detail on many of the things I cover in the review paper that I share with Marta, so people can also take a look at that paper and then send me a question offline. I know. Anyway, so let me. So this is the search, free, and all I wanted to say here is that there are 3 types of gravitational wave emission that we studied. There is the one produced by slowly rotating progenitor, the one produced by rapidly rotating progenitors, and the one produced by very exotic models. And the more realistic one that people believe in terms of abundance as well in the local universe are the slowly rotating progenitors models. And those are neutrino driven. And the left plot shows roughly where the efficiencies are standing for the all-free data, which is already an understatement compared to the sensitivity when are 4. We are probably a factor 2 or 3 better in terms of the distance we can detect them, and these are expected to be ballpark 99% of the supernovae that happens out there, at least if we think that they go like the ratio of neutron star remnant versus magnetar remnant. And then on the other side, you have the extreme emission model where you expect that you can have like a failed supernova where a chunk gets absorbed back and produces like a signal as strong as an inspiral, or an elongating long bar where the proton neutron star elongates like an ellipsoid and rotate. And those are models you can detect it at much larger distances, but you're also able to exclude them much more easily looking at the data. And the exclusion probability is never 100% because you have the data that you're searching that have gaps where the instrument was not in science mode. But I don't know, these are roughly in the middle, you have the gravitational wave that are produced by rapidly rotating progenitors, and they are getting more and more interesting, but the reliability of the waveforms is a little bit less currently than the slowly rotating ones, in the sense that the introduction of magnetohydrodynamics in the simulations, the codes are a little more recent, and we didn't have as much comparison between different groups. I would say that in the slowly rotating progenitors, there is a fair amount of agreement in some of the features, even if the amplitude sometimes they disagree. And the rapidly rotating and the extreme models, the one that are on the right plot, are type of emissions that we can't rule out completely, but the theorists say, okay, if you get it, great, but don't trust it as much. One thing that is going to be interesting to keep track for the rapidly rotating one, and we have to see, there are some results from Martin Obergallinger in Valencia. He calculated some waveforms from rapidly rotating progenitors that were so much more energetic than the slowly rotating one, that the visible volume was 2 orders of magnitude larger than the visible volume for slowly rotating one. And if you start having 2 orders of magnitude more in the visible volume, you might overcome the fact that you expect 2 orders of magnitude less in abundance. But these results were on 2D models, and other people are trying to reproduce the same results on 3D models, and obviously for all the simulations, I know it takes time to have them run, and is computationally enormously expensive. I know it's not like CBC that you produce 100,000 templates and go. I know here you wait for the 2 waveforms a year, and I know I was talking with a couple of years ago with Kei Kotake in Fukuoka, and they were very, very proud that they were able to introduce the full-fledged general relativity in their simulation, not just a conformally flat. And he said, we just published this paper where we calculate the first 50 milliseconds of the gravitational wave emission. And I was thinking, whoa, so since the gravitational emission is at least a second long, it means you need 20 papers to send it out, the whole waveform. And so it's a little bit of a challenge. So these are the comparable results for free data for the all-sky search, comparable sensitivities. I'm not going to go too much into the details, but people can have a way to interpret the results. There are also efforts of people that are trying to combine neutrino and gravitational waves, sometimes even just using the timing of the interesting triggers. And this is an effort where they're trying to do something different with the waveform morphology. This is the work is led by the Rome group and Håkon Andersen that is currently in the O'Connor's group in Stockholm. And there was a question from Marta about this candidate, and the only thing I can say is that the best association with the galaxy is something that is order of 200 megaparsec away. We don't have any model that can detect any of this family of supernovae at that distance, so I'm not going to say much about it, but that's unfortunately all I can have to say. The part I wanted to spend a little bit of time is to talk about this area of parameter estimation, and this is because most of the papers that has come up are in the last year and a half, 2 years, and not everybody might be informed about it. So there are, the idea is that to identify in the gravitational wave features that are deterministic and that can be parameterized in some ways, and then try to learn astrophysics from these features. And just to give an example, this is a typical example of a spectrogram which has some of the feature visible. And on the right, there is a little bit of the landscape of the feature that you can have. There is from the left to the right, looking at the sketch to the left, you have the prone convection, core bounce. Core bounce, I said those are the free peaks that I mentioned earlier that are templatable. Then there is the high frequency feature, and this is related to the proton-neutron star that has not lost all the proton and electron. And so there is a little bit of residual Fermi pressure that prevents the radius to reach the asymptotically, 10 or 20 kilometers radius. And so it takes order of a few hundred milliseconds to complete the capture of the electron with the protons. And so as the radius shrinks, the size of the proton, the frequency, the fundamental resonant frequency of the proton star goes up. And this feature is interesting for a number of reasons, because the slope depends on the equation state, and we already published a few papers about it, the initial slope. And the asymptotic value will depend on the final mass of the proton-neutron star, and the upper limit of the asymptotic value might give information about the upper limit in proton-neutron star. In observation, the people have not been observing proton-neutron star above 2.7 solar masses or something like that. Neutron star, and so the upper limit of this frequency could give information about it. There's also an interesting aspect related to the rotation, in the sense that if you have a rapidly rotating progenitor, the centrifugal forces will slow down the capture process of proton and electron, and will make this slope a little bit flatter, so the growth rate should be slower. And then there are, on the bottom right, three type of features. There is the memory that I just mentioned, that even if it has in asymptotically zero frequency, the ramp up while it develops is part of it is in the visible band for interferometers. And then there is the standing accretion shock instability, which is a feature that was originally observed by the Oak Ridge group. And this is very interesting because it's the first example of a neutrino plus gravitational wave parameter estimation methodology, and I'll say a little more about it.
Can I interrupt there?
Absolutely.
I just want to correct and say the SASE was discovered at NC State. So.
Oh, interesting. That's very good. So thank you. So I don't make any, can you send me a reference?
There's an original Blondin and Mezzacappa paper.
Okay, that's wonderful. The reason why I said I said Tennessee. Yeah. Oh, I misquoted that. I knew it was Mezzacappa and Blondin were the authors. Thank you. Thank you.
Yeah, we're just very proud of it. So
No,
I
no,
just want to make sure.
and I wanted to do it right. I wanted to do it right. I know that Blondie and Mezzacappa were involved, and so thank you. I just misquoted. I knew it was them. Anyway, I don't have anything scripted. Otherwise, I would have said it right. Thank you. Thank you. I know. Don't say to Mezzacappa, I misquote. He's gonna be very mad with me.
It'll be fine. Be fine. Tony's a nice guy.
Don't write me out. But yeah, okay, yeah, no, and you, I work very well. We have a very good working relationship with Zacapa. The paper is with him. There are a few papers, so thank you, thank you. So and this plot is actually from Mezzacappa, the one to the right, from Mezzacappa's group, and this is one of the tricky thing, which is the association of the modes and the inference you might want to do with that is tricky because you might get different inference on the property of the neutron star depending which mode you are doing the association, and which mode is the dominant one might even change with time. And the high frequency feature also, yeah, that's a common one. Well, anyway, let me go through them with more detail one by one. So I said a few words about the high frequency features, and this is a paper with some of the results. Let me talk about this the SASI a little bit. I mentioned these spectrograms, and the one to the left, you can see that there is the high frequency feature is the vertical or almost vertical part, and the black blob on horizontal describes the SASI. And one thing that we worked on, and this was with a group of Cecilia Lunardini and Zidu Lin, and Zidu is just started his faculty position in China, and I think is in the group of the SIGO, but I'm not sure exactly which location. But we did two kind of a methodological paper. One about can we detect the presence of the SASI, and by looking at the neutrino signature and looking at the gravitational wave signature. And the second thing, can we estimate the frequency? And basically the idea of the detection is to calculate the relative energy in the high frequency region where the SAS is located with respect to the total energy of the event, and use that as a metric for detection purpose. And these are histograms, example of histograms. If you have an injected gravitational wave in red that has the SAS in it, and in blue if there's no SAS. And so the idea is that you take this energy ratio on the time frequency region of the SAS versus the total energy, and you choose a threshold, and no matter what is the threshold, I know there is a false alarm probability that you might say there is SAS even if there is not, and a detection probability of the SASI, which you rightfully claim is there. So you can produce these receiver operating curves, and you can do something similar also for the neutrino side. And I obviously encourage people to look at the paper in the neutrino side. And the philosophy of the data analysis is slightly different in the sense that the noise in the gravitational side is from the Earth, and the neutrino side is related to the Poissonian fluctuations of the neutrino signature. And so when you are, if you have a signal that has intrinsic fluctuation itself, when the signal is very close, you're going to see the neutrino luminosity going up and down, and there are several papers that present that. I don't know. We use for this paper for these plots from numerical simulation from the Keiko Take group. But I don't know. I've seen this oscillation in several other papers. And so the tricky thing is that if you're close, you're going to have that the what control the fluctuation of the luminosity is in bigger part related to the intrinsic fluctuation of the signal. And if you go further away, is going to be related to the fluctuation, the Poisson fluctuation of the neutrino detector itself. Michele, go ahead.
Hi, I may have missed a point here. So from this equation here, can you, so where does the luminosity enter? So
Oh, the equation doesn't contain the luminosity.
so how does the uncertainty couple with uncertainty on the frequency?
Okay, so this is for a different topic. The equation is for the parameter estimation. So I will go back to the equation later. Let me start in explaining maybe the plots a little bit slower. I know I have a lot of material to cover, so I'm going a little bit faster. So do you understand? Do you want me to re-explain the plots? So maybe that would help a little bit.
Yeah, that's right.
Okay.
Thank you.
Okay. So if you take the neutrino signature, and there is the peak at the beginning, and then it starts going down, and then if you wait at least 100 milliseconds after, that's when you can develop the SASI. And when you develop the SAS, if you look at the signature, they start having some oscillation. They go up and down, and these oscillations are oscillation due to the fact that the SASI precesses around the proton-neutron star, and what happens is that the parts of the proton-neutron star where you have impinging material, where you have an enhanced production of neutrino, as this region rotates around a certain axis around the proton-neutron star. And now the proton-neutron star is relatively opaque with respect to the neutrino, which means that if the observer is on the side where there is a little more neutrino production, you see the more neutrino. If the side where there is neutrino production is on the opposite side, you have less neutrino that go to the observer. And so this is the physical region of the oscillations. This is also the region why certain groups believe that if the observer is equatorial with respect to the axis of rotation of the SASI, you will have a difference in the frequency of the gravitational wave SASI component and the neutrino SASI. Some people expect a factor 2 in the difference between the gravitational wave frequency and the neutrino frequency of the SASI component. And there are different papers try to quantify what is the range of frequencies. And I prefer not to go into the details of how they establish the range of frequency, but I know the paper here has some of the references, but they expect for the gravitational wave to be of the order of 50 to 200 hertz, and for the neutrino side maybe half the upper limit, the lower limit, they're about half than that. The relationship between the frequency of the SASI in the neutrino versus gravitational wave might also be dependent on the observer. I've seen papers from the Garkin group where they were observing that if you are along the axis of rotation, they are almost identical, and if the equatorial, the dominant component is when one is double the frequency of the two, which is almost intuitive, because if you are along the axis, this issue of the obscuration of some of the neutrino that are emitted from the proton star is not there. So this is about how the frequency of the two are related. In terms of gravitational wave, the frequency is related to the detectability of the SASI, because if the gravitational wave frequency is lower, is going to be in a region of the noise where seismic vibration have a bigger role, so it's harder to detect it. And if the frequency of the size is higher, it might be closer to the sweet spot where you are more immune to vibration of the ground. For the neutrino side, the frequency of the SASI is not as important in the detectability. Is the distance of the source that is more important, because the amplitude of the Poissonian fluctuation is the relative amplitude with respect to the signal goes like 1 over the square root of the number of neutrinos. And so if you are closer, 1 of the square root of the number of neutrino is a smaller number, which makes the intrinsic amplitude of the SASI oscillation more visible with respect to the noise. But the frequency dependence of the noise is not as drastic like in the case of gravitational wave. In the gravitational wave, you have a order of magnitude variability between 10 hertz and 100 hertz, which is an issue. Does this clarify a little bit what you were asking?
Perfectly. Thank you so much.
Okay, wonderful. Okay, and now the beautiful thing that we observe in the paper, and I will not go through in the detail, is that when you produce this receiver operating curve in the detectability of the SASI separately in the gravitational wave and in the neutrino, and then you try to do them jointly, the joint one is better than both of them. And at least for the case of the data that we used for this paper. And we are in the process of writing another paper, but this for me was a great encouragement that every aspect of parameter estimation for supernovae where we could do neutrino and gravitational wave joint parameter estimation, we should explore that. And we have not done that for any other example systematically than in the case of the SASI, and hopefully this talk is an inspiration to some of you to interact with some people in my community. Obviously, if you have any idea you want to share them with me, I'm always able to talk. And we are working very closely with Cecilia for the case of the SASI, but I think the case of the high frequency feature is another interesting one, because I've seen simulation with the different grow rate, for example, of the resonant frequency of the protein to star, depending on the equational state, and different neutrino emission as well. The key thing is that I believe that there will be features where things are more promising and features where things are less promising. I was working, for example, for one of the papers with Mike Pakios at Caltech, and he was trying to check the variability of the neutrino luminosity in the pulse part, and he didn't see much variability in the initial pulse. But if anybody here has an opinion that there is more variability there, I know that would be wonderful. These are the example of estimation of the frequency. And this the reason why I'm excited about this plot, and this is based on gravitational wave, but we have a similar plot in the neutrino, is because if you want to verify the hypothesis that one is double than the other, you don't need to have a very high precision in estimating the frequency. So that's, for example, one thing where I'm very excited that we wrote this paper for the joint estimation of the parameter of the SASI, because I think that it could help to prove that hypothesis or see what we can do. There is still more work to be done for the duration, and the duration could be useful as well, because a long duration should be helpful in understanding if it's more likely that your supernova collapse in a failed supernova, or if the SASI had a big role in the explosion or not. I'm not going to go too much about the memory also, because I know the only thing I wanted to say is that people were fairly skeptical for a while that the low frequency component of the spectrum of the noise in gravitational interferometer would allow to detect the memory. I'm very proud that we show that we can, even if it's going to be dependent on the model. So, for example, rapidly rotating progenitor are expected to have a much larger memory because the axial nature of the rotation can produce very non-spherical emission, and if you have a very prolate or very oblate explosion, you expect the development of a large memory. It's also important to notice that the memory for supernovae is expected to be radically different than the memory that people talk about in black hole merger, because in that case, the formation timescale is order of milliseconds, and here order of a second. So in that case, it goes, the center frequency of the ramp up is very low frequency and not as promising for gravitational interferometers. There is also another thing that is worth mentioning, that for the memory production, the interferometers at those frequency, the noise is not of fundamental nature, meaning, Heisenberg determination principle, it's technical nature related to aspects of control that can be improved and are in the process of being improved. So I think the future is bright for the memory, not just because of improving the data analysis software. In this case, we were able to do what we were able to do because we had better linear predictor filters, but also because the hardware and the control can be improved. There are other efforts, and if you go in the conference webpage, you'll see a number of efforts where people try to have a software that discriminates between slowly rotating and rapidly rotating progenitor. A few things about the future. I know we have a lot of online information, and I hope that this talk, is a stimulation to have, more of this conversation and maybe even more systematic coordination of the community. I know what we have is already a great start, but when we were at the conference, we had a lot of aspects where we realized that, there is more that we can do. And as a matter of fact, we have, the open call for our community to discuss some of the electromagnetic issues actually right after this one, and they have to connect to that one. But so this observing plan that is available, and for the ground-based interferometers, and the one thing that you can see is that O3, we wanted to have 100 megaparsec, and then O5, 240 megaparsec in terms of detectability binary black hole. But this is a nice number because it tells you how the noise rescales. So it means there is a 2.5 reduction in the amplitude of noise. And then if we go to third generation, it's going to be an order of magnitude more. The last slide I wanted to share is give you a little bit of a perspective of detectability in terms of brute force calculation of the energy in a specific band for different emission models. And so the way you read this plot is that you have different types of supernovae, the models. In the bottom right, the black circles are numerical waveforms from mostly slowly rotating one, and then the yellow one at the top are the one from the most optimistic models, and then the slanted lines describe which energy can be excluded with different runs, and for different distances, and this gives you a little bit of a perspective how things will evolve, and I think the message here is that for O5, we almost all the model will be detectable within the galaxy, because 10 kiloparsec, the fact that we can exclude those energy, it means that there are very few models that we will not be able to detect. But we don't know what nature will provide. O'Connor, Couch used to tell me that the emission model like snowflakes. So anyway, that's it. In terms of construction, LIGO India will come up, and obviously we have the third generation that is more longer term, and Kagera is a little bit uncertain what's going to be the long term in terms of performance, and so there is a lot of planning and politics that it's above my pay grade. So I was thinking to close the talk here, and thank you for the attention. And if there are any question, I can talk about it.
Thank you very much. That was very interesting and a lot of new information. Any comments or questions?
I see a couple of questions. Random order. Alec, you are muted first.
Yeah, no, I was probably also above your pay grade, but we all heard of the crazy funding situation involving only having one LIGO antenna. Has that been resolved, or is it still a dangerous thing?
No, I don't think it's a problem in the sense that if there would be, first of all, this year there's not been change in the funding of the interferometers, and if they would do a cut in half of the interferometer budgets, the plan is to freeze the upgrades and keep running 2 interferometers until future elections.
Okay, thank you.
So no one is planning to close anything. We have a lot of expensive upgrades that would be delayed to leave the operation going.
Okay, but delaying those is better than stopping operations with something that really works well. So, yeah.
And Nora had a question, I think.
Oh, I didn't. I was just clapping.
Oh, okay. Okay.
Thanks a lot. It was a great talk.
Yeah.
I have a question if no one wants to jump in. So of course, LVK will get an alert from SNEWS should there be a galactic supernova, and so that really helps in the detection of the gravitational waves. The question that I have is, how well can a supernova be located on the sky?
Okay. Yeah, that's something I didn't touch on this just because the papers that we have done on it have been already out for a few years, but the ballpark is a little bit model dependent, but a few, I would say if it's galactic, a few square degrees ballpark. For a galactic distance, that's the ballpark, few square degrees.
And that information would be shared.
So that information, that's actually part of the things that we should probably coordinate between the community, because there are aspects that have not been finalized, not even internally. I know, for example, people say, okay, if we go in detection mode, we need to have a paper out within a month. But then the full detection mode doesn't mean that we have a candidate that is 3 sigma, or would we go in detection mode if the candidate is 2 sigma, or if we have no candidate that is I don't think there is a final plan for that, but I think it's something that can be discussed and should be discussed. So we have I think we have a representative in the neutrino community that are writing this white paper after the conference to decide what are the things we should coordinate in the case of galactic supernova, and this maybe is one of the topics. So if you have any representative of your community that wants to participate, please contact me or any organizer of this workshop or the chair of the supernova group, or I could suggest that if you have a representative who wants to come and give a talk in our open talks, talking about your wish list, I think might be a good thing to coordinate some of these things, because it takes time, because the community have to discuss the science case and ponder things in many different level of interactions. So I don't want to say things as above my pay grade, but I think this is a wonderful topic to discuss.
Yeah, I completely agree. One of the things that SNEWS wants to do is not only issue an alert that a supernova has occurred, but also try and pinpoint on the sky where the supernova is just from the neutrinos. And some individual detectors can get a few square degrees, but also SNEWS as a network can also get a location on the sky just from triangulation. Any information that we could get from the gravitational waves about where the supernova could be fed into um, that process or that analysis of trying to identify where the supernova is, so that the astronomers can point their telescopes in roughly the right place and catch the shock breakout. So
Yeah,
I think there's useful information that we can get from gravitational waves.
yeah. I know that they release the estimate of the sky location for binary candidates, and I think it's good that if it's done also for supernovae. I'm not sure if there is software that is already approved for automatic release for the sky location, assuming is a supernova, because the current default might be that they run the CBC software and not the one that assume is a supernova. And the other question that could go in the other way, and I was discussing this with Cecilia, is that this neutrino sassimeter releases a confidence that there is a SASI in the signal, even just from the neutrino signal. I don't know, would we able to get in real time or relatively quickly release a statement on the neutrino sassimeter? But if the neutrino luminosity are released fairly quickly, I know we can estimate in matter of hours or minutes. I know, but definitely these are kind of things that I think would be really, really good to discuss, and they deserve obviously a focused discussion that it doesn't get justice from just a question at the end of a talk. They deserve that. I know we have initial conversation, and then the people that have I would say initial conversation, white papers, and MOUs. That's the progression. Yeah.
Yeah, I wanted to comment on that because when I was doing the neutrino follow-up with O3, I remember that for the two candidates that we had of being supernova, it was indeed coherent wave burst that was running by default, and it was not providing any location, at least for
Yeah.
O3.
Yeah, and that's something that we can talk about, and I'm gonna report this question to the burst group and to the supernova group chairs for conversation, and then we will probably I know it's gonna be the supernova chair that will contact someone on your side. I know, as I said, I have been the chair of the supernova group, but nevertheless, I know we have like every collaboration, internal layer of discussion and approval, and the key point, and that's why we organize this conference, is that there is good science that needs more coordination. We need to continue the coordination of the community that was started, and so I'm not going to put a percentage of how far we are from the optimality, because I don't think I can do it. But definitely there is more coordination and understanding that I think we should invest time on.
Yep. Indeed. So I see now a hand by Nora.
Yes. Thank you. Now I had thought about it. So this is I guess, a follow-up question to what James was asking. And since I joined late, maybe you mentioned this, but I was curious to know, how do you think the Einstein telescope and all the future, I guess, space-based telescope would be able to help with localization? And what do you think they would do better or worse compared to LVK?
Okay, with respect to what?
With respect to LIGO Virgo Kagura.
LVK. Sorry.
Yeah.
I didn't, I want to make sure I didn't hear
Yes.
Super K. Okay.
No, not Super K. No, I'm from Ice Cube, so.
Okay. So you should expect, for example, for Cosmic Explorer, order of magnitude better sensitivity. So I think, and then Australia is thinking about to develop high frequency instrument. I know Einstein telescope, and the space. So I think in terms of direction reconstruction, there will be some improvement. Maybe we can go down to, I don't know, half a square degree, something like that. I don't think it will go down orders of magnitude. And there will be an improvement in the detection range. My dream, and I don't know if we will reach it with Einstein telescope and Cosmic Explorer, my dream is if we can also reach for rapidly rotating progenitor a detectability in the Virgo cluster. And because if we are able to reach the detectability in Virgo cluster, we're going to have order a few supernovae a year. And so we can, count that not just galactic supernova, but, every decades have a supernova detected. And that would be my dream. But that would require also some more investment in hardware research, because the current plan for development future instruments has been focusing on the sweet spot of around 100 Hertz, because it's the one that works now for binary systems. Supernovae, the bulk of the energy is few hundred Hertz, where larger laser powers are the biggest benefit. And if you want to have larger laser powers, then you have to be careful about heat dissipation, vibration induced by pressure, and you need to have bigger mirror. You need to have bigger suspension cables that are more difficult to insulate from vibration. So you have to say, okay, maybe we should have instruments that are focusing more on supernovae. And since we already made the people study binary system happy, so the third generation has non-trivial technological challenges if we want to make it optimized for supernovae. But I feel they are worthwhile. Obviously, they have the great benefits. I know they say, okay, we like the idea of being able to detect primordial black holes, so we can tell if there are black holes that are not formed from supernovae at all, or do mass spectroscopy. But I feel that the supernovae are the Higgs boson of the gravitational wave field. It's the next big thing that I would be happy if people try to actually chase actively, not just as a byproduct of already existing infrastructure. But we'll see. I think as I showed in this plot here, this plot here, if you take the 05 run curve and you lower that a order of magnitude, it means that there's no existing model of emission that will not be detected from Einstein telescope or Cosmic Explorer. So it means all the the black circle will be above the corresponding curve for Einstein telescope comet explorer. So the detectability for a galactic event is almost guaranteed. At that point, it would be interesting to see what we can do in terms of parameter estimation, because let me go up. Maybe I'm still sharing the screen. Let me go up to this plot here. I know some of the detailed structure. I know here there is a slightly changing slope that I know that is due to the fact that you switch the mode, and maybe we can do some of that reconstruction, and so definitely parameter estimation will benefit a lot, because as when I showed the reconstruction here, I know this one is a good reconstruction. I know we have situation that we still detect very well, but I know it looks much more sparse, the coherent wave-burst event, and it gets a little more challenging making more accurate statements about the progenitor. I would say that maybe read also the paper I review for next level in depth, and I'm happy to talk more. But I hope this gives you a little bit of a glimpse.
Yes, thank you very much. It would be awesome if we can one day get to that we can actually do parameter estimation, or at least constraints.
Yeah. I think we are already at the case where some can be done, and in the papers, in that paper referred to several, but we are, I would say, in the fairly early stages, because we are still trying to map out also the detailed degeneracies. So like, I know, the slope of the high frequency feature has some degeneracy with respect to equation of state and rapid degree of rotation. That should not be a big problem, because I don't know, we know that the rapidly rotating are going to be more rare, but I know we are at the stage where we want to map out where the noise is the problem and where the degeneracy of the parameters is a problem. Ricardo?
It's getting a bit late, so if I can also postpone my question to email. So I don't know, Mark, as you prefer.
Whatever, if you want to ask a quick one, and then we call it a day. But thank you guys for all the questions. And if people want to have a conversation even offline, they can send me an email. I can do a Zoom.
Yeah, I think you can just go ahead for a quick question.
Sure.
And then, yeah.
Yeah, it's rather straightforward. It's a basic one. So from what I remember, and I think from part of your talk, it seems the definition of T0 is quite important to distinguish from models, and even for the search in the parameter of the whole template and so on. And I was curious, because this T0 very easily can come from the neutrino observation. How sensitive, or what's the precision that you need for this T0, and does it depend on that precision? Or is, for instance, the uncertainty between the neutrino T0 and gravitational wave start more than whatever we can already achieve?
So I think there is two issues here. So let me give a little bit of landscape. So if you have only the electromagnetic observation, I know our Onslow window are much longer than the temporal separation of the beginning of the gravitational emission and the peak of the first neutrino burst. So those the definition is not too controversial there. I know
Right.
You assume they're roughly at the same time.
Yeah.
On the other side, when we let's assume we have a neutrino trigger, and in that case the issues are different, in the sense that we can use the time of the neutrino trigger to search a much narrower interval. And currently, we would not narrow it down just for the search, much less than a couple of seconds, even if the beginning of the gravitational wave might be constrained much more precisely than a couple of seconds with respect to the peak of the neutrino. This is because, first of all, you don't know which part of the gravitational wave will stand out first. The prompt convection phase is expected to happen within maybe 10 milliseconds or even less. However, the prompt convection phase might not be the most energetic in terms of gravitational wave emission. The turbulent phase that might happen 50 to 100 milliseconds after for slowly rotating progenitor is the first one that we expect to detect. And so in that case, if we catch that and we catch a neutrino, then we can use the temporal separation to learn some astrophysics from how long did it take the shock to stall and start becoming turbulent. And so that's the delay as a physical meaning that we can use. If you have a rapidly rotating progenitor, those free peaks, the core bounce is expected to be within 1 or 2 milliseconds. And so in that case, the time of the peak is good to know very precisely, and we can learn some precise astrophysics from the temporal separation of the two. There is also another issue related to the turbulent phase, which is that our digital filters sometimes blur features a little bit, because if you have a wavelet component that has a duration of 20 milliseconds, that wavelet components will not give you timing more precise than 20 milliseconds. And on the other side, if you have a wavelet component that has a resolution of 1 milliseconds, then you're going to be more precise. So I would say there are certain astrophysical aspects that we can learn from the timing, and definitely the beginning and the end of the SASI feature, even if it's not related to the neutrino, can be useful for search more carefully in the gravitational wave side. So there is good astrophysics in learning the timing, but it's more in the interpretation of the candidate, I would say, than in the detection side. The detection side, you can give us a time, and the precision that we have is that if you have an error of few milliseconds or 20 milliseconds, we will, for detection purposes, we will do the same things. But for interpretation of the astrophysics of the source, we might use them in a different way.
Okay, that was great. Thank you. And lovely talk.
Yeah, and we can talk offline. Any other question? So the only things that I have to say is, as I said, James, don't write me out with mezza kappa or that I misquote that. It will not happen again. Thank you, everybody. It was an honor to talk with you.
Well, thank you for coming to talk to us.
Thank you.
Yeah, thank you, Michele.
Okay.